All right, let's see how this goes. Trying something different. This is going to be on the iPad. Basically, it's going to show a few different things on the iPad, and this is all about NMR. And this one's going to be about carbon NMR, and it's to do with the carbon-13 atom. And if you've listened to the podcast, you'll have an idea of why it's all about the carbon-13. Can't be carbon-12 because it's an even number of nuclei, and we need an odd number so we can get that unbalanced spin happening. So anyway, moving on to this. These are spectrums of two different molecules, and we're going to look at why they come up like this and why our spectrums look similar to this. The first one on this side here is ethanol. Ethanol is simply a 2-carbon chain with a OH group coming off it. And what I've got down here is this is a very, very basic looking table of chemical shifts. There's a bigger one that you'll be given, and it will cover a whole bunch of other stuff, but this is just a really basic one just to try and get you in the idea of how we're going to look at this. So we see we have 2 peaks. That means 2 carbon environments, so 2 carbons that are not the same. Ethanol, as you know, only has 2 carbons in it, so these carbons must be completely different. Looking here, we've got a chemical shift of about 58-ish. So we look at our table of values and went, all right, between 58, we must have a C bonded to O. So this guy here tells us it's a C bonded to O. And this guy here, because it's down there between 0 and 50, tells you it's a C bonded to C. From this, we get an idea that we have 2 carbons, one bonded to another carbon, and the next one is going to be bonded to O. From this, we get a skeleton, and we go fill in our hydrogens, and we'll just put a hydrogen here, 1, 2. We fill in hydrogens to make our bonds happen. And when carbon can have 4 bonds, so you have to have 2 hydrogens here, and 3 hydrogens here to make 4 bonds. And our oxygen has 2 bonds, so therefore we must have a H there. And that really makes sense with this spectra here. Moving on, we get a bit more complicated. We get this spectrum, and we can see that we've given a chemical formula, and I'm just going to go through which peaks here represent which carbon down here. So we've got 4 peaks, which means we have 4 carbon environments, 4 carbons acting differently. And I'll just get a highlighter. And we're going to look at 2 peaks here within the 100 to 150. So if I just move this back here, so you can see 100 to 150 down here means it's a C double bond to C here. So we must have at least a C double bond C for that to happen. 1 carbon down here, this guy here, because he is below 50, here's just going to be a C bonded to another C. And up here, way up here, up above 150, this must be, based on our summary table here, a C double bond to O. Putting this together, we can work out which carbon belongs to which. Moving on to, so I'll take another colour, I'll take green. I'll say this guy here, he's been a carbon, double bonded to another carbon. He must be one of these things. We're not too sure which one he is, but he must be one of those peaks there. Moving on, we've got another carbon here. This carbon has a double bond to another carbon, so I'm going to put him as red. And this guy must come from this peak here, because he's a carbon double bonded to another carbon. This carbon here, you can see this carbon has a double bond to O, so therefore this carbon must be up here. And moving on to the next carbon, I'll do him in pink. This carbon is simply just a single carbon bonded to another carbon, so he must be the guy down this way here. So that's looking at how you can identify which carbons there are there. The next one is going to be a bit harder, where we're not given the actual structure of what it looks like. We're going to have to try and determine the structure based on a spectra. So here we go. So what we've got is a molecular formula of C4H10O. Now, we say which one is it going to be? And we've got a spectra here, and the first thing you should notice is it has 3 lines. Now 3 lines here, and 4 carbons in our molecular formula, that tells me I have to have symmetry somewhere with this molecule. I'm going to look up here and see which molecules might have symmetry. Now, first of all, I look at this A, and I go, all right, we've got a long chain of carbons with an OH at the end. This basically tells me that there's going to be no symmetry whatsoever, because each one of these carbons is going to have a different, going to be affected differently by this OH group at the end here. So it can't be this guy, because we have no symmetry. If it was, hang on, I'll erase this. If it was this one, what we would see is 1, 2, 3, 4 carbons being different carbon environments, and we'll see 4 different peaks in this spectrum. Moving on to this one here. All right. Again, we have 1, 2, 3, 4 carbons in a chain. Now this carbon is very close to this one here. This carbon's one off it. This carbon's one off it, so it looks like it's going to be similar, but he has one attached to this guy here. So there's no symmetry in this one either. Because there's no symmetry here, what you're going to see is, again, 4 different bands on this spectrum. Moving down to C, what we've got here is an OH at the end, 2 bonds, 2 carbons. Then we have a branch off to 1 carbon here and 1 carbon here. Because we have this, what we've got is a line of symmetry down. I'll just try and draw it in. I'll zoom in. What I've got is a line of symmetry down here, where this carbon with 3 hydrogens is 1, 2, 3 away from the oxygen, and this carbon here is 1, 2, 3 away from the oxygen as well. That means these 2 carbons, if I just highlight them, this one here and this one here, are in a sense going to be the exact same carbon environment. So these guys are just going to form one peak because they're the same distance away from their oxygen and they have nothing else after them. We can redraw this so it's a bit easier to see as having an OH at the top, bonded to C, and moving down like that. I can't really say that very well. I'll try and do it a little bit better. Erase all that. I have OH to C, then to C here. And you can see that we've got a line of symmetry straight down the middle, where this carbon and this carbon are going to be the same. So this guy is going to form 1, 2, 3 peaks, which fits with our spectrum that we have. So this guy could be, look at this one, what he's got is a line of symmetry down the middle here as well. Actually, he's going to have, here's OH, where are we? OH, bonded to carbon, and he's got 1, 2, 3 carbons off him here. Each one of these carbons is the same distance away from the OH, so each one of these carbons is going to be the same environment. So what he's going to form, he's only going to have 1 and 2 carbon peaks. So based on that information, we've got the right answer, is this guy here, because of the symmetry lines. Oops, erase all that. Alright, so the only one that would form these 3 lines would be this one here, because he's got the 3 carbon environments. This one's got 4 environments, this one's got 4 environments, this one only's got 2 environments, this one is the right one. If we look at this a bit closer, we can see that we'll have 1 carbon here, which should be within around about 50, between 50 and 100, and we have 1 which is in between 50 and 100. We've got this carbon here, which is bonded to another carbon, single bonded. So these two here should be just in there, okay, just within that this range between 50 and 100. So that makes sense for that one to be that there, based on how many carbon environments they have. Moving along, we've got a bit harder one again. Using the simplified table, try and work out what this, Try and work out what this spectrum is. Okay, so basically what we see is it's a carbon 4, we've got 4 carbons, and we got 1, 2, 3, 4 peaks. So that means we have no symmetry, which is good. So each one of these carbon peaks is going to be a separate carbon environment. It's going to be one of these carbons. So let's have a look at what we got. We've got one carbon up here, which is very, very, very high up. It's above 150. And if you go back here and look at what 150 meant, it meant a carbon double bonded to an oxygen. So let's bang in here a carbon double bonded to oxygen. We've got one of those. Within here, we've got 2 carbons which are in a range between 100 and 150. Basically, that means we've got 2 carbons which are going to be double bonded to each other. So that's all right there. And we must have, down here is one which is above 100 and just above 40 there, about 50-ish. This means we must have 1 carbon which is bonded to an oxygen. All right, so there are carbon environments. We've got 2 like this, okay, and we've got 1 like that. So let's try and jigsaw piece our puzzle together. Right, so I'll try and zoom out. I'm not too sure if I can do that actually. I'll just try and draw it over here. I'll zoom in over here. So what we must have is we must have a carbon double bonded to oxygen. We're going to have a carbon here, double bonded to another carbon. And we must have another carbon bonded to oxygen out here. So let's put in our hydrogens. How many hydrogens up here? Got 1, 2 hydrogens here. We got 1 hydrogen here. 1, 2, 3, 4. No hydrogen on this guy. And what do we got? A hydrogen here. Another hydrogen dismiss here. And another hydrogen here. So let's see if this fits in. We've got, see if this works with our empirical formula or our molecular formula. 4 carbons, 1, 2, 3, 4, 4 carbons. 6 hydrogens, 1, 2, 3, 4, 5, 6 hydrogens. 2 oxygens, 1 and 2, and that kind of makes sense there for our molecular formula. So this is what it could end up looking like. Alright, this is one alternative for this molecule. Another one, which is the correct one, is if we swap this O and this C around, we'll get something similar to what we want. Now, if we go into carbon, double bonded to carbon, which has to be correct because that's the only way that can happen, bonded to and up to C, a H there, and put an O here, then over to another methyl group. What we end up with is exactly the same number of atoms in each thing that we need. So it's the same molecular formula, but what we see is a difference in functional groups here. Here, what we've got is an alcohol group or an aldehyde group. And here, what this functional group is, this is an ester. And looking back at where these are, this thing here is a double bonded to O at about 170-ish, a little bit less than 170. And if I go back to my intense table here, what we get is a breakdown of where these double bonds can happen. Now, our double bond O in an aldehyde happens at this, I can't draw on this one, but it happens at about 190 to 120. Whereas a double bond to O in an ester, where we have a single bonded to O on the same carbon, is around 170-ish. This is consistent with where this line is here, and so therefore this double bond to O here must also have a single bonded to oxygen here. And that's where it can get a bit messy. But for this, what you'll need to use is a better table than this small one here, and that's the type of table that you'll actually be given in your exams. You'll be given something more along the lines of this, and even a bit more detailed than this one as well. So what you can look at is going back to here. This double bond to O, depending on where it lies above the 150 range, is what type of double bond to oxygen you'll get. If it's up here, you might get a double bond to oxygen with a H group off it. However, when it gets lower like this, you're going to get double bond to oxygen and a single bond to O. And I should have known that before I wrote this one down. Anyway, I'll do a couple more of these and then I'll see how you go on that. So give me 2 seconds and I'll just find some more. Alright, so now's another example, and we have to try and work out the structure of this molecule. We're given a molecular formula here of C4H10O, and we're told that it's not an alcohol. So it can't be an alcohol, but we need to work it out. So we've got an O in there, obviously. So where is it? What's going on with that O? We look at our chemical shifts and we see that it's in this region, so that O must be bonded to a C. And it must be, why did I do that? For the O must be bonded to a C, so it must be C bonded to O somehow. And it's not an alcohol, that means it can't be OH, can't be that, so what it has to be is going to be bonded to another carbon. The next thing, well, what I should have done first is said, right, there's 4 carbons here, there's only 2 peaks here. That means there must be some symmetry in the molecule. There has to be one C bonded to O, and there must be a C bonded to C somewhere in it. And there must be symmetry about somewhere to make that work. Now looking at this, we have a C bonded to O based on that, and a C bonded to C. Because it's not alcohol, it has to be C bonded to O bonded to C. The way we're going to get symmetry from this is by putting 2 more carbons on either side. 2 more carbons on either side basically means we have a symmetrical molecule around here. This carbon environment here is going to be the same as this carbon environment. This carbon here is going to be the same as this carbon here. And we're going to have a peak at carbon bonded to oxygen, which we have here, and that's going to be the same, so that's good. We have a peak at carbon bonded to carbon, which is carbon bonded to carbon. We have a peak here as well. So this, we bang in our hydrogens, which will be here 1, 2, 3, 1, 2, 1, 2, 1, 2, 3, and we count them up. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, C4, 1, 2, 3, 4, C4, H10, and our O in the middle. We have our molecule, which will be CH3, CH2, OCH2, CH3. And that's based on understanding the symmetry about somewhere, understanding that we have a carbon bonded to oxygen here, and a carbon bonded to carbon here. It has to be symmetrical, it's bang over there, and this must be our molecule. Now, this is Carbon NMR, and as you can see, it's pretty straightforward. It's just putting in what you have and jigsawing it together until it makes sense. There is, next up, hydrogen NMR, which is a bit more detailed and you get more information out of it. And yeah, you can basically get structures a bit easier with less confusion as to what they might be with hydrogen NMR compared to carbon NMR. And that's what I'm going to get onto now. If you have any questions on this, give us an email, give us a yell, but hopefully what you'll understand is it's just a matter of writing down what information you have and piecing it together to make sure it makes sense with the spectrum that you have.